We will now discuss today one of the very important consequences of ideal MHD, which is this effect called magnetic flux freezing. Okay. Ideal MHD essentially means the main thing to note regarding ideal MHD is that there is no resistivity. It's in this sense that the magnetohydrodynamic system is ideal. There is no resistivity, or equivalently the conductivity is infinite. Okay, and infinite conductivity. So, as a consequence of this particular assumption, it so happens that there is this effect called magnetic flux freezing, alternatively sometimes called the Alfvén flux freezing theorem. And before going into the detailed discussion of that, we should sort of tell you what it really means in practical terms. What it means is that magnetic field lines in ideal MHD, okay, as in if the ideal MHD conditions are satisfied, the magnetic field lines are frozen into the flow. Okay, frozen into the flow, into the fluid flow, okay, which essentially means that if you have a streamline of fluids like this, okay, that would be the fluid streamline, the magnetic fields also would look like that. It would coincide with the streamline. Okay, so this is one thing. This is one way of looking at it. The other way of looking at it is that the magnetic field lines are frozen in, but more properly though, in other words, the preceding definition was kind of a loose statement of Alfvén's flux freezing theorem. More properly, what it means is that the magnetic flux which we denote as phi, okay, which is essentially the area integral of b of, I will say b, which is a position of both, which is a function of both position and time. Yeah. Sorry, I sometimes write a and I sometimes write s for the area element, and I often get confused between the two. So in this case, I am writing a. Yeah. So this is conserved. This is the real statement of Alfvén's flux freezing theorem. What this means in effect is that consider a flow, right, where for some reason the cross section of a magnetic flux tube is changing. For some reason, yeah, and the magnetic field is essentially the number of field lines per unit area. So the value of the magnetic field is essentially the number of field lines per unit area. Okay, and what we are saying here is that the integral of the magnetic field dotted with the cross sectional area is constant. In other words, here you see out here the area is smaller. And so if the area is smaller, well then, and if the flux has to be constant, then the magnetic field has to be larger. You see the area is smaller where the flux tube is constricted. Okay, therefore if the flux has to be the same as what it was out here, yeah, it follows that the magnetic field itself out here high B, relatively speaking, this would be high B and this would be low B. Why? Because same flux. Here and here. Okay, the flux is the same, that is what this statement is saying. The flux is the same, yeah. However, the cross sectional area, and when we say area, we are really talking about the cross sectional area like this. This area, this cross sectional area is larger here than there. So, therefore, there is only one way the flux can be the same here and here, and that is if the magnetic field is higher than it is here. Seen from the point of view of magnetic field lines, essentially what it is saying is that, well, you know, the magnetic flux tube constricted somehow for some reason, I do not know why, but it did. That is what the flow is doing. And we also said that, you know, the magnetic field lines follow whatever the flow is doing. That's you know, they are frozen into the fluid. So, it follows that the B field lines will look somewhat like this. In other words, the field line density, but really the area density, number of field lines per unit cross sectional area is higher here as compared to here. The field lines are squeezed together, they are more concentrated. Okay. That is simply a consequence of the fact, you can look at it as a consequence of the fact that the flux is conserved, either that, or you can look at it as a consequence of the fact that the magnetic field lines are frozen into the flow. So, the flow is for some reason getting constricted, and well, you know, field lines have to obey the flow. That is what Alfvén's flux freezing theorem is telling you. Okay. So, this is one very important property of magnetohydrodynamics. It turns out that there are many other conserved quantities in MHD. Well, mass is conserved, so on and so forth, all is fine, but even with regard to magnetic field and such things. Okay. For instance, magnetic helicity. Which would be the quantity A dot B, okay, ds or so on and so forth, where this is the magnetic vector potential. Which is to say, curl of A gives you B. We have not really discussed this much, but this is the magnetic helicity. It turns out this is also something that is conserved. Okay, there are many other quantities in MHD that are conserved. For instance, one important thing, one important quantity is the magnetic helicity. We will concentrate our attention right now just on the magnetic flux. Okay, so the magnetic flux is conserved in ideal MHD, and ideal MHD essentially means that you know, the conductivity is infinite. Okay. Okay, now you remember everything, pretty much everything in MHD has its roots in the magnetic induction equation, which is this, right. The time rate of change of magnetic field is the curl of V cross B. So, this would be the fluid velocity, velocity field, which is which is prescribed, and I will write this down, but I will explain what I mean by this word, which is prescribed. In other words, what I mean by this is that I am not solving for the fluid velocity field in this case. Okay, and this is V and B are the primary variables in MHD, as we have repeatedly emphasized. For instance, the current density J, which it does not really have an independent place in MHD, so to speak. It's simply a derived quantity. It's simply taken to be a shorthand for curl of B, right? V and B are the primary quantities. Of those, we generally take V to be a prescribed thing. We don't solve for it. We say, well, this is the fluid velocity field right here. Okay, now given a certain magnetic field that is embedded in this fluid velocity field, I don't want to know how the fluid velocity field came about. I don't want to solve for the fluid velocity field, at least as of now. Okay, the simplest way of understanding these things is to say that the fluid velocity field is just given to me by someone. Okay, so it's prescribed. Now the induction equation is going to tell me how this velocity field evolves with time here. How it evolves with time in response to this velocity field. Okay. Now this is ideal MHD, so there are no resistive terms. There is no grad squared B kind of resistive term here. There's not, so because the conductivity is infinite. So turns out that the alpha in flux freezing theorem is a direct consequence of this induction equation, and let us try to see how. And for that I will need to draw a certain picture, and it will take me a couple of minutes to draw this. I request you to bear with me. I thought it's better to do this on the board rather than show you a slide. So this would be, these would be the velocity streamlines. Okay, which for some reason you have a larger cross section here and a smaller cross section there for some reason. I don't know why. Okay, so now let us consider a cross sectional sort of a like this, yeah, and like that. I really should be dotting it here. If I dotted it there, then I should dot it here as well, and so let me do that. Okay, I erase this. So like that. That's what I meant. Okay, and so what I'm going to do is I'm going to call this length element small s. This is bad notation actually. The length element, okay, this is really should be L, but anyhow, and so this would be a cross sectional area S of t, capital S. Okay, so the cross sectional area at time t is, this is cross sectional area. So the cross sectional area at time t is some S of t, and this little small s is the length element along this perimeter, and this is a cross sectional area at time some t plus delta t, S of t plus at some time t plus. So this would be, this is how the area element looks like at time t, and this is how the area element looks like at time t plus delta t. In this particular case, the area element has shrunk with time, but that's not necessarily always true. It might have expanded. As such, it's completely general. Okay, and the fluid is moving with a velocity v. So the difference here would be v delta t. That would be this length. That would be this length. Okay. And I call the area of the side surface, in other words the area of the cylinder, the side, I call it sigma. Okay. And as with everything, this delta t is really small. So, although there is a squeezing, and this v delta t is quite small, so you can idealize this to be a straight cylinder. Okay, as long as everything is really small. So it's in the usual calculus kind of sense. Yeah. So just to re-emphasize, these are the velocity streamlines. Okay, and these two loops are separated by a time interval delta t. Okay, between this and that. So this is the loop at time t, and this would be the loop at time t plus delta t. Okay. Now, the difference in flux magnetic flux, okay, through the loop, yeah, in the two instances. In which two instances? Well, this and that. Okay, in the two instances is delta, because I am saying difference in flux, I write delta phi. Yeah, this is equal to, and by going by the definition of phi, phi is essentially B dot dA, isn't it? So phi, delta phi is integration over the cross sectional area at t plus delta t. Yeah, the magnetic field, which is a function of position and time, and the time is t plus delta t, mind you. Yeah, dot ds. This would be the phi at t plus delta t. This would be here. Yeah. So we are now looking at the difference in flux. So the phi at this instant minus the phi at this instant, and we've already written down the phi at this instant. Now what's the phi at this instant? It's quite simple. The same kind of expression, except instead of s at t plus delta t, I just have s at t. Yeah, and instead of b at r t plus delta t, I just have b at r and t. Right? And it's an area integration. So what's the difference between these two? Well, the cross sectional area has changed, and we have allowed the magnetic field to change. Really, that's the main difference between these two. Okay. So let us now call this, let us say that this is equal to some I1 plus I2. In a minute we will ask what is this I1 and what is this I2. Okay. So we need to be very careful about this, which is why I am proceeding slowly. Okay. So where I1 is equal to, I1 is essentially the difference in flux due to the change in the loop position, and I will write this down and then we will discuss it. Like that. The loop position is changed. Now, what's the difference between this piece and that piece? You see the integrand is the same. The integrand is b r t plus delta t. Here also it is b r t plus delta t. What's the only difference between this piece and this piece? This thing. The fact that the S, the area you are integrating it over, has changed. Here it was t plus delta t, here it's t. So, this is the change in flux due to change in loop position. Let me erase this, it is not very nice. So, due to change in loop position, like that. So, the only difference between this and this, like I said, is the difference in the area over in the cross sectional area over which it is being integrated, and in other words the difference between this area and that area. Okay. Whereas, in reality the magnetic field is also changed between here and here, but I am pretending that it is the same. I am pretending in this particular case I am saying that the magnetic field is the same as what it would be, what it is at t plus delta t. So, I am taking the same magnetic field here, which is the B at t plus delta t, and using it here also. Okay. So, this is not entirely physical, but we will see why I am writing it down like this. It is a change in loop position. So, because I want to write down one chunk which is exclusively due to change in loop position, and another chunk which is exclusively due to the change in the magnetic field. I want to split it up like that. Okay. So, I1 is the change in I1. This is really the delta phi. I mean, this is the basic thing. This is what we want to check, and we know that eventually we are going to show that the change in flux, the difference in flux, is 0. Okay. So, but let us write this down. Okay. And I am writing this down as I1 plus I2, where I1 is the change in flux due to the change in loop position, and I2 is a change in flux due to the fact that the magnetic field has changed. Okay. So, we have already written down I1, right, and so now let us write down what would be I2, and I will write down I2 as so you see now the integration, the cross sectional area over which I am integrating will be the same, will remain the same. You will see this. Okay. Whereas the magnetic flux itself is I will change the magnetic flux. So, here it is R B at R t plus delta t, that area integration, minus, I will keep this the same, I will keep the area over which I am integrating, I will keep that the same, but I will change the B. Okay. And so, this would be the change in flux due to change in B at a fixed position. So, you see the interpretation is as follows. In the first chunk, which is this, which is I1, yeah, I was taking the same B in both the integrands, and I was only changing the area over which it is being integrated. In other words, the changing flux due to the change in loop position. Okay. And so, the interpretation there would be I am taking the magnetic field here, okay, and I am using the same magnetic field for this cross section area, although technically that is not correct, but we will see that it all cancels out. The second one, for I2, what I am doing is I am keeping the loop position fixed at S of t. In other words, I am not changing the loop, I am just keeping the loop position fixed, but I know that the magnetic field has changed. So what I'm doing is I'm keeping the loop position fixed, and I'm calculating the change in flux through the same loop, okay, between the magnetic field due to the change in magnetic field. You see, the magnetic field is one value here and it's another value here. Simply due to the change in magnetic field, I'm trying to see what's the change in flux. And really, so the change in flux can be is because the main thing is that the change in flux is due to the change in loop position as well as the change in magnetic field. Okay, and you can see at the end of the day you wanted B RT plus delta T, dot ds at st plus delta t minus B RT dot ds at s of t. And if you look at I1, this is essentially the first chunk here. Okay, this is the first chunk here, and the second chunk is this. Okay, whereas in I2 you will see that this is the first chunk and that has a positive sign. This exact chunk, this exact thing has a positive sign in I2. So when you add up I1 and I2, this guy vanishes. So all you're left with is this and this, which gives you what you wanted. And so that's why we're saying that delta phi is equal to I1 plus I2. Okay. The reason we're doing is this way, in this slightly convoluted way, is that there are certain simple physical interpretations of I1 and I2, and it's a little easier to arrive at the physical interpretation of I2 first. Okay. The physical interpretation of I2, which you remember is the change in flux due to the change in B at a fixed position. Okay, so the time rate of change in B is what? dB dt. Yeah. So the time rate of change in B is d, yeah, but of course partial because the magnetic field is a function of both space and time. So I would write, so the change in flux due to the change in B at a fixed position. So this is the change in B, and of course I would have to integrate over cross sectional area, yeah, like that, yeah, and of course this gives me the total over a fix. So this gives me the rate of change of flux, but what I want is not the rate of change of flux, I want change in flux itself, for which I should multiply by a dt, and this is I2. This is a physical interpretation of I2. Okay. The physical interpretation of I1 is slightly different, but anyway, so we will leave this here. So for the time being we will stop here. Thank you.